It is 2 in the morning. I already solved. This one was way too easy. Today's daily. It's like, yeah, I solved this one like a while ago too. I solved it June of what the fuck? Okay, so I'm gonna solve this one because this one looks fun. You are given a tree with n nodes numbered from 0 to n minus 1 in the form of a parent array parent, where parent I is the parent of the ith node. The root of the tree is node 0. Find the kth ancestor of a given node. We'll reset the timer. The path from that node to the root node. Implement the tree ancestor class. Okay. So tree ancestor, get kth ancestor, get kth. So int n is equal to that. Parent equal to that. 3, 1, 5, 2. Okay, so when I get kth ancestor, so the first ancestor of 3, I start at 3, I go to 1, and then it returns 1. The second ancestor of 5. Okay. 5, so the first one, the second one is 0, and then the third ancestor for 6. Ooh. So it does say tree, and I'm gonna use the restroom, hold up. Okay, I'm back. So it doesn't say, it's a binary tree, and it's not balanced either. So I feel like I can't just be cheap, even though in this area it does work out where I'm like 3 is greater than the amount of levels I have. Because I would actually have to like do a depth first search. So what if we just say, I don't know why n is a factor here. And then this n is equal to n, this equal to parent. Okay, so n is equal to parent.length, right? Yeah. So why is that even given? I don't know. Okay, so get kth ancestor. So let's just say int I is equal to 0. Int cur is equal to node. So while parent node does not equal -1, and I is less than k. We'll say I plus plus cur is equal to parent cur. We should probably switch this to cur, huh? And then we'll just return parent cur. Would this work? It does not work. Oh, let me get out of this. Output 0 minus 1. Okay, wait. Okay, so if I actually traverse this, 1, 2, 3. Would I just say cur? So cur is equal to 3. So while that is not equal, okay, so I plus plus cur is now equal to parent cur 0, 1, so it's 1. Ooh. Yeah. So it's at 1, which points to this, and now I is equal to k, so it returns 1. So why is it not returning minus 1 here? Oh, return I is equal to k cur minus 1? Would that work? Okay. So if I submit this, it's gonna say something weird because a hard isn't this easy. Right? So I think the problem is eventually there's gonna be like a million different nodes down here, and I'm going up, and well, like not even that, I'm just recomputing like these paths. So I think, is this a DP problem? I'm gonna cheat. Okay, DP. So this is, what if we have a new DP, right, where DP of ij is parent for or is parent for ith node. Yeah, so it's the jth parent for the ith node. So this dot dp is equal to new int n by n. Go. Don't know why it's such a big deal though. So how do we actually fill our DP table? We can't just have -1, can we? I want to fill it. We need a base case. So what if we go for int I equals 0 plus n, I plus plus, or int j equal to 0, j is less than n, j plus plus? We can say the dp ij is equal to, I don't know, j is equal to 1. We're not asked for the 0th one, right? Yeah, k is always gonna be 1, so we'll just say, if it's equal to 1, the first parent, we'll just say parent of I. Minus 2. So minus 2 indicates. Haven't found that yet. Okay. We'll keep this. Hmm. Hmm. Okay, so like, I want to say if DPIJ, because we'd want to build this like bottom up. Unless I just built it bottom up from here, starting from leaf nodes all the way to the top. That seems kind of excessive. Is that the solution? I hope that's not the solution. Well, some other times easier. If I did, how would I even do that though? If I just pre-computed everything, I said return. I feel like that kind of seems wasteful though, because okay, if n is your limit on what value n can be, it'll be at most 50. Wait, 50,000? 50,000 or 5,000? That's 50,000, right? 50,000 queries, and n is less than or equal to 50,000. That seems kind of excessive because, yeah, okay. So it's probably not that. Who knows? So starting from current node. I'm gonna say if dp node k is not equal minus 2. Oops. Okay, but I want to say that, but then we're gonna be starting up from, let's say we already have from k minus 1, like 1 to like k minus 1. Then we call get k node k, and then we'd start from the bottom all the way and then go up. So maybe the move is iterate backwards from k. That doesn't sound right either. Okay, so like here, the second ancestor from 5 is equal to the first ancestor of 2. Could I just do this then? Okay, give me a minute. Okay, you know what? Maybe I will try just filling it top, bottom, because then I'm gonna say fill DP 0 -1. Right. So maybe instead of thinking about this as J, we think about this as K. Hmm. Hmm. Wait a minute. Okay, so the second parent to this is equal to the first parent of that. So for I node, dp of I, the kth node, so the first parent is 2. Equal to... Would that work? I feel like that wouldn't work. What? Oh. Oh, right. Wait, not alright. Sure. Let's see what it actually tells me. Okay. So fifth. N equals 5. Huh. Yo, what the fuck? Okay, hold up. Let me just... Okay, let's just go for some classic debugging. Okay. Memory limit exceeded. How the fuck? Are you dead ass? I can't have an n by n matrix. Right. That's fucking awesome, dude. Well, how do you reckon I solve it then? K is less than or equal to n. You're done the move. I don't wanna be friends. Is there a way for me to look at the queries themselves to try and do this? Nice. This can't be fucking real, dude. Well, I feel like I did it, it's just taking too much space. How do I optimize the space? Like, would this even help? Oh. Dude, this executed in 2 seconds. I guess it does make sense. If there's a 10,000, right? How much would a 10? It's a big number. But I wonder if... I wonder if it would solve the other ones except the memory exceeded one. That's my question, if I'm just... the answer is wrong or if it's just not optimal enough. I don't think this one even performed much better than the other one. Heck, this one did better. I want to optimize the time on this one. Will it tell me the answer? Okay, wait. Okay. There's a couple minus ones in here. So maybe there is a way for me to figure out if a query is, how do you say? A query is unreachable. So how do I do that? How do I know that this is on the 3rd level? So if k is greater than or equal to 3, then I return -1. That's a good question. I don't report this one. Okay, part two. So this is a day or two after I originally tried solving it. I got sick, but so initially I wanted to say int dp, and then we'd say dpij is jth ancestor of node I, but this means we'd be storing an n by n matrix, and realistically our tree depth will not be of n, it will be some like, I don't know, the max it would be is like some log of n. So apparently I was just supposed to know what binary lifting was when I went to solve this. I did not. I had to read about it. And the idea of binary lifting is basically you kind of have these jump edges, because we could say um, any integer n can be represented as the sum of powers of 2. So rather than storing like all n ancestors, we could just say store the 2 to the j ancestor, and then we just keep jumping by powers of 2. So this is not only way more efficient, it's like a log n. Traversal, we also only store like something like log of n whatever in our matrix. So I get to implement that now. So with all that in mind, so in DP, so that's our DP to store our 2 to the whatever something ancestor, and we need a int max. So this is going to record the max depth of our tree, and we get the max depth by first setting it to 0, and then the amount of times we can shift the bits of n, like max is less than or equal to n. We just want to see how many times can we add like I believe that's what it's doing here. We're trying to see how many like 2 to the whatever jumps we can make with n nodes. So we'll just say max plus plus. That means dp is equal to new int. Is this music too loud? I feel like it is. Anyways, dp is equal to new int n by max. So this saves a ton of space, and then we'll just fill our dp table. Int k is equal to 1. K is less than max. K plus plus for int I equals 0. Do I even need 0? I'll just say 1. I is less than n. I plus plus. Because I'll just say arrays.fill dp 0 minus 1, and actually I need to fill my base cases, so int I equals 0, I is less than n, I plus plus will say that dpi of 0, the first 0th parent, is equal to parent of I. That works out. Anyways, so now we need to fill our dp table, so dp of I and j, we use the recurrence relation. We need to make sure that the kth is a valid ancestor too. So when you say dp, oh not k, it should be k. So if our last kth ancestor was minus 1, or like we're too deep, we're trying to dig too deep, we just say dp of that is minus 1. Otherwise, oh, this should be a question mark, I'm a fraud. Otherwise, we get the ancestor of the kth node. Previously, this is the kind of double jump that we do. I'm explaining this really badly. We get the k minus 1 parent of our ancestor. It's like a double, like if I had to explain it, it's like a double jump. It's a double jump. And actually, that should be it for a constructor. So we get the amount, like the max amount of times we could jump from for through end nodes. We set up our DP table, we set our base cases, and then we fill it using this recurrence relation. So now it's time to actually get the kth ancestor. So this is where we actually jump through each node. So I think you could technically binary search this. I didn't want to implement that because the guy in the video said that it didn't make a difference in performance, but whatever. So for int I is equal to 0, I is less than max, if we can perform a jump, so if one I forget what this operator is called. I should know that. I is set within our k. So if we can actually make the 2 to the I jump. Fortunately, Java doesn't let me just use 0 or 1 as a boolean, but we'll just say node is equal to dp of this, of the ith ancestor. So we go back, and if node is equal to -1, we'll just return early. We don't want to keep going if the node is -1. Otherwise, we just return node. And don't break, please. Yes. And hopefully this submits well. And yay, I solved it. It was such a... It's a really cool algorithm. So I'm really glad I tried this one. Bye, guys.